Alright folks, this video is going to cover lesson 3.4b over even and odd functions. Okay, the whole lesson today, the point is to be able to prove algebraically whether functions are even, odd, or neither. Okay, but before we can do that, we first have to understand what it means to be an odd function, what it means to be an even function. So we're going to talk about these in a few different ways. Okay, the first thing on your little chart here that you have is talking about symmetry. Well, even functions are functions that are symmetric over the y-axis. Okay, really that's reflection symmetry, so I'm going to go down here and jot that down. This is reflection symmetry. And I'll abbreviate that a little bit. Okay, so reflection symmetry over the y-axis. Okay, because if we look at the y-axis here, you'll notice this right-hand side will reflect right over to map onto the left-hand side. Okay, well, odd functions are different because they're symmetric about the origin. Okay, so the point 0, 0, okay, is included on this particular graph. Okay, but it just means that we can take part of our graph and rotate it. Okay, rotate it down to the other portion. Okay, so this is different. It's not reflection symmetry, it's rotational symmetry. Okay, and it's not any degree of rotation, it's actually 180-degree rotation. That's what it means to be symmetric around the origin, is 180-degree rotational symmetry. Okay, so transformation, we've looked at a little bit with scale changes. Last time we switched the order a little bit. We said s of x comma y equals negative x comma y. That was the reflection over the y-axis. X negative y was reflection over the x-axis. Well, on this one, notice our even function had reflection over the y-axis, so that's a negative x value. Okay, our odd function with symmetry around the origin, rotational, is actually going to flip both of the values there. Lastly, this function notation, it's going to deal a lot with how we prove these algebraically, so it's very important. Okay, it says f of negative x is the same thing as f of x, and we'll talk about what that means here below in a little bit. Same thing over here, it's f of negative x equals the opposite of f of x. Okay, so to understand this piece a little bit better, okay, you have a bunch of empty space below. We're going to draw a little bit of a picture. Okay, so under even and odd, we will redraw these pictures and add some more details. Okay, so our even function, we're going to look at y equals x squared, the basic parabola. And for our odd function, we're going to look at y equals x cubed, the cubic function. Okay, so we will sketch this as best we can here, a parabola, so that we can talk about some of these points and really understand the function notation here. Okay, so let's put some points on here. We know that 0, 0 is part of our graph. Okay, if we plug in 1 and square it, we get 1, so 1, 1. If we plug in 2 and square it, we get 4. And let's do one more. If we plug in 3 and square it, we get 9. Okay, so the points 1, 1, 2, 4, and 3, 9 should appear on our parabola. Okay, let's get some negative values as well. If I take a negative 1 and I square it, I get a positive 1 again. If I take a negative 2 and square it, I'm going to end up at the same 4 that was over here. And similarly, if I take a negative 3 times a negative 3, I get a positive 9. Okay, so let's take a look at these points using function notation to understand what that up in our chart actually meant here. Okay, so f of 0, okay, there's no positive and negative there, that was just 0. Okay, but let's look at both the f of the regular x and the f of the negative x for each of these points. So positive 1, we had a y value of 1. Negative 1, we had a y value of 1. Okay, so both the positive and the negative 1 gave us the same y value. Okay, similarly, f of 2 gave us a positive 4, but so did f of negative 2. And finally, our last one there that we have on our graph here, f of 3 gave us 9, but so did f of negative 3. Okay, so up above you are told that an even function, using function notation, f of negative x was equal to f of x. And that's all this is saying. When I plug in a positive x value, I should end up with the same y value as if I plug in a negative because of this symmetry over the y-axis. Okay, symmetric across. Alright, so let's check out what happens with an odd function. Cubic goes through the origin as well, but it is increasing, like this snake shape from left to right. And we'll put some points on there as well. So we've got 0, 0. If I take 1 and cube it, I get 1. If I take 2 and cube it, I get 8. 2 times 2 times 2. And if I take 3 and cube it, I get 3 times 3 times 3, which is 27. Okay, we'll do the same thing for our negative values. Negative 1 times negative 1 times negative 1 is a negative this time. Okay, that's why I'm below here instead of mapping back up. If I take a negative 2 times a negative 2 times a negative 2, I get a negative 8. And then finally, negative 3 cubed is negative 27. Okay, so let's look at our points in function notation again. F of 0 doesn't do a lot of good for us helping-wise because we can't see any sign when it's just 0. Okay, but let's take a look at f of 1 and f of negative 1. Okay, well f of 1 was a positive 1. F of negative 1 was negative. F of 2 was a positive 8. F of negative 2 was a negative 8. And very, very similarly, our last two pairs of points, f of 3 was 27, and f of negative 3 was negative 27. Okay, last time when we plugged in opposite x values, we got the same y values. So we're going to look what's happening over here. We plugged in opposite x values and got opposite y values. Okay, they're the same magnitude, they're the same size, but they're different values. One's positive, one's negative. Okay, so if you go back up to your chart, you'll see this notation. It says f of negative x. So when we plug in the opposite, we get negative f of x. Okay, recall that f of x is just a fancy way to say y. So it's saying that if I plug in the opposite x value, I should get the opposite y value. Okay, so this 1 and the negative 1, they were opposites all the way down. Okay, so when that happens, we have this 180-degree rotational symmetry. If you plot or if you connect the point that are matching up, you should get a straight line through all of these points. That's the 180-degree symmetry. So, let's talk definitions. We've got even and odd. Now that we know what they are, let's write it down. Okay, definition, even is a function that has reflection symmetry over the y-axis. Okay, that's geometrically, and algebraically we will say it is even if f of negative x is equal to f of x. Or vice versa. Okay, and then it is odd, geometrically, if it has 180-degree rotational symmetry through the origin. Algebraically, if f of negative x equals negative f of x. Okay, so go ahead and pause the video and make sure you get those definitions down. And I would like you, while you are doing that, to go ahead and grab out your parent function note card. We're going to talk about our 9 parent functions that we have on there, and we will identify whether each of those is even, odd, or neither. Taking a look at our pictures here, we're just going to go through them one by one and talk about their symmetry. Since we have graphs, that's what we'll do to decide whether they are even, odd, or neither. Taking a look at the identity, we have the point 0, 0. We need to ask ourselves, is this graph showing rotational or reflection symmetry, or neither of those two things. Okay, so definitely not reflection symmetry because I do not have a branch up here. Okay, rotational symmetry is happening though because I can take that part of the graph up top, rotate it 180 degrees down to the bottom. So this one, since it has that type of symmetry, we're going to consider it odd. Okay, the next one is a parabola. We just talked about that as our example for even, so hopefully we know that is an even function. Okay, you'll notice it has reflection symmetry over this y-axis here. Okay, let's look at the greatest integer, the step function here. Okay, it looks very close to the same shape as the line, so we might think maybe it has some rotational symmetry. Okay, but when we take a closer look, I know that it starts at 0, 0. If it has 180 degree rotational symmetry, this open dot would be mapped 180 degrees to right over there. Okay, you'll notice that point, negative 1, 0, is not on the original graph. Because of that, it does not have rotational symmetry, so it cannot be odd. It definitely does not have reflection symmetry over the y-axis, so this is an example of neither. Okay, what I would like you to do is go ahead and take some time to look through those other ones and see if you can decide whether they are even, odd, or neither based on their graphs. Alright, hopefully we decided that a cubic was odd. Of course, we already had that example. Okay, a hyperbola, I can take this whole branch, rotate it 180 degrees and get down here, so it is odd as well. Inverse square is even because of the reflection symmetry. Square root is neither because you can't do any sort of reflection or rotation with that thing. Absolute value is even, and our exponential is another neither. Okay, so take a minute and make sure you get each of these examples, their names, listed under the even, the odd, and the neither on your class examples here. Flipping over to the back side, we are going to prove, okay, I told you the point of this lesson was proofs. We're going to prove algebraically whether functions are odd, even, or neither. So let's remind ourselves of what these things mean. Okay, in order for it to be even, I'm going to go kind of backwards here. In order for it to be even, we know f of x will be the same as f of negative x. Okay, odd, by definition, function notation, that f of negative x was equal to opposite of f of x. Well, neither, of course, then would have none of those statements being true. Okay, so what we're going to do is go in the order that I kind of just explained. Notice we're given f of x. Well, f of x, the first thing we can do is look at, well, what is f of negative x when I simplify that? If they're the same, then we're done, we know it's even. If not, then you have what f of negative x looks like, so we can see, is that the opposite of f of x to decide whether it's odd. Okay, so our first step is decide, is it even or not? Second, if we have to, if it's not even, we'll go see if it's odd. Then finally, if it's neither, we'll know it's neither even or odd. Okay? So f of x here, we've got 8x to the fourth minus 3x squared. We're going to take a look at f at negative x. Okay, so just like we've got in our equation in x here, we need to switch all of our x values with a negative x and just simplify. So 8 and then negative x to the fourth power minus 3 times negative x squared. When we simplify, I'm going to write it again, we got to know what each of these are, so just bring that on down. Negative x to the fourth power, negative times a negative times a negative times a negative, ends up being positive. So I've got a positive 8x to the fourth. Okay? If I take a negative x and square it, I've got a positive x times a negative 3, so minus 3x, bring down that squared. Okay, so now our job is to compare the f of x with the negative or with the f of negative x, okay? So our original with this one, and see if they're the same. Okay, you'll notice here I've got 8x to the fourth minus 3x squared, and that's equal to our 8x to the fourth minus 3x squared. They're the same. Okay, so we are going to write that f of x was equal to f of negative x. Therefore, that was our first test. It's got to be even. Now, we know the symmetry for even functions. Okay, they have reflection symmetry over the y-axis. And we're done with that proof. Okay, taking a look at the second one over here, we've got f of x equals 6x cubed minus 9x. Our first thing we look at is f of negative x. Okay, so I've got f of negative x equals 6 times negative x cubed minus 9 times negative x. We need to simplify that so we can compare. A negative times a negative times a negative ends up being negative, so negative 6x cubed. I've got a negative 9 times a negative x, so that's plus 9x. We'll compare these two to see if they're even. Okay, notice I've got a positive 6x cubed and a negative 6x cubed here, so these are not equal, so not even. Alright, so we're done with our first test. Now we have to look at, we have f of negative x, we need to look at negative f of x. Well, this is just the opposite sign of everything we see up here, so let's write it. Negative f of x is the opposite sign of everything that's going up here, so this changes to negative 6x cubed. This negative 9x changed to a positive 9x, and we're supposed to compare that to the one right above it. Okay, well, you notice those are equal, so let's say that. We will say f of negative x equals negative f of x, and according to our algebraic definition here, that's what it takes to be odd. So therefore, odd. Okay, so I'm looking for all these steps in your work. This is a proof, okay, not like our T-chart proof days, but we are organized in a line here, and you got to give me a statement. How did you know it was odd? How did you know it was even? What'd you look at? Okay, so this one's odd. We know the symmetry. It's rotational, so 180-degree rotational symmetry. And it's always through the origin. And I'll just call that 0, 0. Alright, let's take a look at the next one. We've got 3x squared plus 5x, that's f of x. Our first job is to look at f of negative x and go plug it in. And of course simplify. Okay, I've got a negative x squared, that's positive, so 3x squared, and then a positive times a negative, negative 5x. We compare that to our original. Notice those aren't equal. The sign on that 5 have switched, so it can't be even. We just have to decide, is it odd? So we look at negative f of x. We got to go up and switch all of our symbols up here. We get a negative 3x squared and a negative 5x. Now, if it is odd, these two would be equal here, so let's check them out. Notice our 3x here is positive and our 3x squared here is negative, so these aren't equal either, so it can't be odd. Alright, so we will say f of x was not equal to f of negative x, and that was not equal to negative f of x. Therefore, it was neither even or odd. Now, here's the hard work. We know the symmetry for even functions, we know the symmetry for odd functions, but we don't necessarily know if there's symmetry on a function that's neither even or odd. Okay, so to do this, we're going to look at what the function is itself and take a look at it graphically. Okay, I'm hoping we can get to a point where some of these will notice what the symmetry is without typing it into our calculator. Okay, but let's take a look for this one. Grab out your calculator, and in your y equals, go ahead and type this equation. We're going to take a look at its graph. Let me get a standard window here. Okay, well, you'll notice this is a parabola shape because our equation itself, 3x squared plus 5x, is the equation of a quadratic function. Okay, all quadratic functions do have some sort of symmetry. Okay, there's an axis of symmetry. Okay, so we have reflection symmetry, but it's not over the y-axis anymore. It's over that axis of symmetry. Okay, if you'll remind yourself from Algebra 2 days, the axis of symmetry is the x value of the vertex, and you can find that by taking the opposite of b over 2a. Okay, if you would like, you can find this in your calculator just by tracing that minimum. Okay, but doing it algebraically might be a little bit quicker for us here. Okay, so opposite of b, negative 5 divided by 2 times a. So we're symmetric over the line x equals negative 5, 6. Okay, so we have reflection symmetry over x equals negative 5, 6. Okay, so all parabolas will have symmetry. They're all going to have reflection symmetry, and it's always x equals that x value of the vertex. Okay, something to remember there. Alright, let's take a look at the next one. We've got f of x equals 0.5x squared, or to the fourth, excuse me, minus 2x squared plus 1. Okay, remember the first step is to look at the negative x and simplify. I'm hoping by now we've noticed a little bit of a pattern. When you take a negative to an even power, it's always positive. Okay, and when we take a negative to an odd power, like over here, it ended up being negative, or switching the sign. Okay, so here, this ends up being positive, so we have 0.5x to the fourth. This ends up being positive, so we take negative 2 times x squared. And just drag down that plus 1. Okay, first job is to compare what we're given to what we have now. And you'll notice those look just the same. And if they are equal, we will say that they're equal. So f of x was the same as f of negative x. And that was our first test for an even function. And if it's even, we know it has reflection symmetry over the y-axis. Okay, and if you want to say x equals 0, because that's the equation of the y-axis, you're welcome to do that. Alright, looking at the next one, we've got x to the fourth minus 5x plus 2. Okay, we are going to plug in f of negative x, just like we have on all of the other ones. Okay, these parentheses are very important. They tell us about what our sign ends up looking like. Okay, so if I simplify here, positive power, or an even power, so it's positive. Here we've got a negative times a negative, so plus 5x, and drag down that plus 2. Comparing that, we notice that they are not equal, so that means not even. Okay, our next step is to see, well, maybe it's odd. So the opposite of f of x, we just switch what we've got up here. So it becomes a negative x to the fourth, a positive 5x, and a negative 2. And we'll compare these bad boys. And our signs are not the same here, so those aren't equal, so it can't be odd either. Alright, so that means it's neither. We're going to say f of x was not equal to f of negative x, was not equal to negative f of x, therefore neither. Make my dots a little darker there. Again, remember the neither may or may not have symmetry. We got to look at the graph. This is x to the fourth minus 5x plus 2. Let's go take a look at that in our calculator here. So x to the fourth minus 5x. You get out of the exponent there. And then plus 2. Now, this kind of almost looks like a parabola. What I'm going to do is kind of zoom in on it a little bit so we get a better idea of what's going on. I'm going to cut out all this extra x value. It'll let us see it just a little bit more clearly what's happening. And now we can see the shape just a little bit better. Now, quadratics or parabolas, they're symmetric through the vertex here. Okay, but we actually have a little bit more action going on here. We've got this extra little curve happening. Okay, because of that extra little curve, this is not symmetric. Okay, we can't draw a line through that lowest point and reflect it over. Okay, it's also not rotational, because that would mean our ends were going opposite directions here. Okay, so this is an example of where a graph does not have symmetry. And we'll just say that. Okay, on our blank here, we'll say no symmetry. Alright, let's take a look at number 6 here. F of negative x equals negative x to the fifth minus 2 times negative x cubed, and simplify. A negative to the fifth power, an odd power, is negative x to the fifth. Here we've got negative to an odd power, so that's negative times a negative plus 2x cubed, and we'll compare those two things. They're not equal, so that means not even. So let's look at negative f of x. Okay, negative f of x is the opposite of what we have up here, so we'll take our positive and switch it. Take our negative and switch it. And compare these two ones right here. Notice that they're exactly the same, so that means our f of negative x was the same as negative f of x, which means for us, odd. Odd always has symmetry. It always has 180-degree rotational symmetry through the origin. Alright, so what we're going to do now is take a look back up at what we've done so far and see if we notice any patterns. We've got some odds, we've got some even, and we've got some neither. Okay, let's take a look at this equation here that ended up being odd. We've got x to the fifth and negative 2x cubed. Over here, that was neither. We've got x to the fourth. This is x to the first. And then we've got plus 2. Backtracking over here, we got x to the fourth, x squared, and plus 1 on the end. Here was x squared, x to the first, ended up being neither. Here we've got x cubed and x to the first being odd, x to the fourth, x squared being even. Well, if you notice, the power, the exponent value, it's being even or odd gives you a clue as to whether the function itself will be even or odd. Okay, so notice here, all of our powers, x to the fourth, x squared, the 4 and the 2 were even, and our function ended up being even as well. Here, they were both odd, and it was odd. On number 3, we've got a mixture of even and odd, a 2 and a 1, and it was neither. Here, we've got 4 and 2. What I want to talk about right here is the 1. Okay, really constants, if you remember, this we could write x to the 0. Now, 0 is neither even or odd itself, okay, but in terms of even or odd functions, constants act even. Okay, so we're going to consider 0 kind of an even number when it comes to checking whether we're doing our math here right. Okay, so constants act even. So that means all of these are even. We have an even function. Okay, over here we've got an even then an odd, so this was a neither. Here both odd, so it was odd. Okay, so we should be able to determine on these last four without doing the math whether they should end up being even, odd, or neither. Now, these are proofs, so of course we have to go through the steps, but recognizing those exponent powers will help us so that we know we're doing our math correctly. Okay, so looking through here on 7 and 8, 7 here I've got a 3, a 1, and really this is a 0. It's a mixture between even and odd, so this should end up being neither. Okay, the next one we've got an odd, an even, and an even. Okay, so this should end up being neither as well. Okay, those last two, see if you can decide what they're going to be without doing the math here. 9 is all even, so even. And 10, we've got a mixture here, so that one should be a neither. Okay, so what I would like you to do is go ahead and pause the video, okay, and I want you to go ahead and prove each of those things for the last four, neither, neither, and then even, and neither. Okay, remember that these neither ones are hard for the symmetry. Okay, so when you're done, we're going to come back and talk about those things. Okay, so on number 7 here, go ahead and check that you have all of this work done correctly here. Okay, proofs, we've got to show all our steps for that. I want to talk about the symmetry. Okay, we said neithers can have symmetry or not. We know that all quadratics will have symmetry. Okay, I want to talk about cubics. This is the equation of a cubic function since our highest exponent value is x cubed. It's the third power. Okay, so let's go ahead and take a look at its graph. It's x cubed minus x plus 3. Okay, and it has this snake shape that all cubics will share. Okay. What's actually happening here is we have a strictly odd function that's actually been shifted up. Okay, remember if we go back up to this equation here, the reason this was a neither was because of this plus 3 on the end. That constant acted even. If you cover that up, or if you don't think about that, this x cubed minus x, right, that's strictly odd, which should have symmetry through the origin. Okay, well, what's happened here is we've had a plus 3, or we've been shifted up 3 units. Okay, so this still should have reflections, or rotational symmetry, but instead of from 0, 0, it's going through 0, 3. Okay, so we have rotational symmetry. And this time, it's through the point 0, 3. Okay, well, all cubics are going to have rotational symmetry, it turns out, because they're all going to have this cubic shape, this snake shape. Okay, there's going to be this point where it changes direction. It's called a point of inflection. Okay, let's take a look at this next one here. We've got y equals 3x cubed plus 2x squared and plus 1. Okay, this one is not strictly odd before the constant. So that means it's more than just a translation up or down. There's been some action left and right as well. Okay, let's take a look at the graph. Now our point over here, again, I'm going to zoom in a little bit so we can see what's going on a little bit more detailed. You don't have to do this necessarily, but you can see our point has moved over just a little bit to the left as well as up, so where it flips over. Now, it's not actually possible for us to find that the coordinate of that point of inflection without calculus. So for us, we only care about what kind of symmetry it has. We won't focus on the point for this one since there is a shift left and right. We won't have to worry about it. Okay, we just have to say that there is still 180-degree rotational symmetry since this is a cubic function. We just don't know exactly where that point is. Okay, so 180-degree rotational symmetry. And we don't have to worry about what the point is through. It's not through the origin, and it's not a shift just up or down, so we don't know. Okay, just focus on what you do know for that one. Okay, number 9 ended up being even. There's the work for that. You should know even always has reflection symmetry over the y-axis. Okay, let's talk again about this shape. We know it is cubic, so we know it has 180-degree rotational symmetry. Just like quadratics always have reflection symmetry. Okay? Now, I'm hoping we can get to a point where we're looking at the equation. Just ask yourself, is this odd except for the constant? Okay? If it's not, if you can't answer that question yes, then that means there's a shift left or right as well as up or down, which means that we can't actually find the point of inflection. But let's go ahead and look at the graph of this thing. So I can show you that it really has been translated a little bit more. So x cubed minus 6x squared, I keep doing that. There we go. Plus 12x and minus 4. So our graph here, the point of inflection is right here. Again, we don't have to worry about what that point is, but notice it does have that 180-degree rotational symmetry. If you extend your window, we'll just do a zoom 6 so you can see it a little bit better, you'll be a little bit more convinced maybe that you can rotate that down 180 degrees to get on that bottom branch. Okay, so for these ones proofs, make sure you have all of the work so that I'm convinced that it really is even, odd, or neither, and then get that symmetry based on your graphing calculator or by the definition. Okay, if you have any questions while you're going through your homework, please do not hesitate to ask.